I had really planned to come over to Berkeley and to the Bay Area and to be there in person, but too many other commitments just did not make that possible. So my apologies that I speak online. And what I am going to talk about today in this first talk, in this first session, is really to give a bit of a background overview history on earthquake rupture modeling and how we use it for earthquake ground motions. Okay, so we'll take a look back into the past very briefly. And then I want to focus a little bit on the spatial variations of on-fault displacement or slip heterogeneity, and then discuss the other ingredients for earthquake rupture modeling and how we came up with certain ideas and let's say how we develop these tools nowadays for creating kinematic rupture models. Then I will add a few other additional constraints that I think are necessary for to be considered for the simulations and observations, and finish off with some open questions. Now, the look in the past obviously will be utterly incomplete, and so I apologize in advance to many that will not be mentioned here in my presentation. And I find a disclaimer in the beginning that I will not provide much detail or review on how dynamic rupture simulations are conducted. I will just present them as they are, where they appear, and what we learn from them. So, from the very early, seismology history on, it has been recognized that earthquake ruptures are complicated. That was already in the 1960s and 70s. On the very left, you see a plot that shows the slip rate or slip acceleration on a point on the fault, as Kay Aki has envisioned it back in 1967. And he also showed that this slip heterogeneity can be described by an autocorrelation function, what he called here of the dislocation velocity. And we hear about these autocorrelation functions a little later again in the presentation. I'm taking this together. He proposed an omega square or an omega -3 model to explain far-field observations. And we all know that Jim Brune took on this information and this work and developed the now famous Brune model that everybody has been using for something like 50 years or more to describe far-field spectral decay and build associate models. About a decade later, Joe Andrews looked at how slip or stress might be distributed on the fault and how they are connected. And so he developed this extended fault slip characterization with a two-dimensional slip function, dxz, that he described with very specific properties. And on the top, you see the slip function, which is a nice Gaussian hill, so to speak, and the corresponding static stress function, which is also well behaved. But if the slip function just becomes a little complicated, a little bit heterogeneous on the left, you see that the stress becomes extremely complicated. He described this slip and stress connectivity connection with the spectral behavior. And the wave number domain he used here, or the wave number vector, is described as K. And so slip function in the wave number domain, he envisioned to decay as something like omega k to the -2. So sort of related to the omega square model I just described for frequency of waves. And so stress and slip are intimately related. And on the right, I show these equations, how we frame them in the Fourier domain. And it turns out that these equations that link stress on the left and slip on the right via a so-called stiffness function turns out to be extremely useful later on for our dynamic rupture simulations and for kinematic rupture modeling. Now, this idea of Andrews was then first really taken up by Art Frankel in his famous paper from 1991, in which he linked the spectral decay of far-field displacement to a fractal dimension and the B values by combining many elementary sources. He called these sub-events, and he developed this hierarchical distribution of these slip patches, as you see in the very left. And by hierarchical, I mean that the size of these slip patches follows a fractal distribution. Adding to this random stress actually self-similar random stress with certain spectral properties, he showed that if the fractal dimension is 2 and the stress drop is constant, which is sort of supported by many observations, that should lead in an omega squared decay of the seismic wave field. And this information of omega squared decay and the connection between slip and stress is something that we both have to feed into our rupture models, but also use to make sure that they are both physically correct and that the output is correct. So the seismic waves we generate should show that spectral decay that we expect from the source modeling. And here I'm just citing two specific pieces of work that used Frankel's idea in the so-called composite source model by Zhang et al. Or Anderson, or the K-square rupture model by Herrera-Bernard, that took these ideas, developed them a little further, and showed that if you in fact have these composite fractal patch models that and slip decays as with the K-square model, you get the right waveforms as predicted from the previous slide. So this is the first set, I would say, of kinematic rupture models that really considered slip, stress heterogeneity, and return waveforms automatically almost with the right spectral decay. Okay, so now I take a step in a different direction. The previous slides really showed theoretical models, and now I want to focus more on observation-based ones. At that time, in the late 1990s, we had many earthquakes that were relatively well recorded. At that time, Northridge had happened, Landers had happened, Kobe had happened, and Chichi earthquake had happened, well recorded. And researchers took those data to conduct earthquake source inversions to develop rupture models, so to describe the slip on the fault and the temporal rupture evolution. And Somerville was, I think, the first one in his famous 99 paper to characterize the earthquake slip from these inversions. So he used about 15 rupture models and then, as shown on the very left, processed these in order to understand how is slip distributed. So he counted what he called asperities, or large slip regions, and did some statistics on it and looked at scaling laws of these asperity properties. And he also compared these slip maps with the K-square model I just described. So he computed the slip spectrum in a very specific way. He constrained it to have a fall off of this K-square that I described, and did some spectral fitting on these few finite fault rupture models that were used at that time. A few years later, this was basically pushed to the next level, I would say, where now, myself and Greg Barossa and Daniel Lavallée and Ralph Archuleta took a lot of rupture models and tried to fit different spatial random field models to these rupture models. We used an autocorrelation function in space, or the power spectral density in the Fourier domain, P of K, which is shown, and these equations are shown on the left here, these random field models for a Gaussian. Let me see if this works. Can you see my mouse? I can show a pointer here. There's a pointer. So we have a Gaussian model, exponential distribution of von Karman. So these random fields models were tested in order to understand how the slip models may or may not be described with these. This was sort of the input, a whole range of slip models. These are, again, these Gaussian or fractal distributions shown as an equation on the left as simple examples. So trying to fit these power spectral density curves, it turns out that the von Karman correlation function best replicates the spectral behavior of slip distribution. And it turns out that the correlation lengths depend on magnitude, and the Hurst exponent in this equation in the top here, h, is pretty constant for all these rupture models that we had at that time. And so correlation length AX or AZ, as shown in this equation below here, and the Hurst exponent now basically form an input in order to do slip model simulations or create realizations of heterogeneous slip on a fault using these autocorrelation functions. I just want to point out that this H of about 0.7 seems to be an interesting number, because exposed slip surfaces at the surface show actually very similar H exponent of the fractal or fractal character of the roughness on the fault. Okay, so as I said, we can use this to simulate slip heterogeneity on the fault. Typically, we assume a fault plane. I would always advocate that you calculate the fault plane using source scaling relations, as shown in the left for a magnitude 7 earthquake. The fault dimensions are not identical because they can change based on, different boundary conditions and so on. Then we simulate the random slip on the fault, and there are Fourier methods, there are geostatistical methods. There's recently Levesque et al. Developed this Cahoon-Loewe expansion, as shown in the center here, which is very useful if you have not a planar fault, but actually curved rupture surface on which you want to model slip. And this was also used by Graves and Piotarka in their work, as shown on the right, and we will see much more of this, I think, during the next 2 days. So I would like to pose a question now, or I would like to alert you that the probability distribution of the slip distribution, as I showed just now, so the 1-point statistics of slip on the fault, in these simulations is actually automatically constrained to follow a normal distribution, a nice smooth Gaussian, which may or may not be true. In fact, Gusev, who unfortunately passed away a few years, has proposed that this slip heterogeneity should follow a modified log normal distribution. Or again, Lavallée and Archer later proposed is a non-Gaussian Levy law. And Song and Dalguer showed that the precise statistical properties of slip govern actually the ground motion. So we need to think about how to model that slip heterogeneity on the fault. And so in a recent work, a former postdoc of mine, Kiran Thinglai-Jam, tested probability distributions using about 400 rupture models from the source model database. And we find evidence that slip actually follows a truncated exponential distribution as shown in the center. So what does that mean? And to illustrate that, I'll show a little example on the right. So if you do a normal slip, let's say Fourier transform-based slip simulation, you get the top figure here in A. That's your slip on the fault. And as you now change, and here's the normal distribution of this one dimension, this the 1-point statistics of the slip. Now, if you change that gradually from a Gaussian to the truncated exponential as going from top to bottom, you see how slip becomes more focused and more concentrated. So the moment doesn't change. The distribution, the spatial variations of slip in itself doesn't change much, but slip becomes much more peaked and concentrated, which again has an important impact on the seismic radiation eventually. And so I think that aspect is currently not fully considered in our rupture model generators. Another thing that is important to consider is the question is, where does the rupture start? When we test our rupture model generators, we usually work or often work with past earthquakes, well recorded. We know where the hypocenter is. Or we run a set of simulations and choose a hypocenter sort of at random, or which we think is convenient, either in the south or north or east or west of the fault. But it turns out the hypocenter location is not random, but it's related to the slip or the stress on the fault. And we showed this in a paper in 2005 using many rupture models. What we find is that rupture starts on or close to a large slip region, an asperity, but it cannot start very far away because of an energy budget consideration from rupture dynamics. And ruptures may nucleate at any level of slip. And so if we take this example on the right here, which is a finite fold rupture model from Greg Barossa for the Loma Prieta earthquake, so we are way past some years old work. The hypocenter of this earthquake is indicated by the star here. Using this argument I just described, these blue stars would also be viable hypocenter positions given the slip distribution. So the rupture starts not too far away from a high slip patch, but it does not start right on top of the maximum slip point. These red crosses would not be viable hypocenter positions because they're too far away from any asperity, and from a dynamic rupture point of view, if you nucleate an event far away from any, let's say, in situ initial stress that sits there, you wouldn't feed enough energy into the crack tip in order to make the rupture propagate. So in a kinematic simulation, you can always do that, but these red crosses would be dynamically non-viable hypercenter positions. So we should not choose them in our kinematic simulations. It would be non-physical. Okay, so at this point, I would like to give you two brief examples from rupture dynamics because we want to look more into the temporal evolution of rupture. So I showed two movies for simple strike slip fault magnitude 7. On the left is a planar fault. On the right, a fractally rough surface. I need to see how I start the movie. Let me see. Okay, I need to get rid of the laser pointer. All right, so a planar fault, the rupture starts. It's nice and smooth, circular rupture. The waves at the air surface are very simple. And now we see the same example, but with a rough fault. And you see the complexity in the rupture process. You see a very complicated seismic wave field. And that's all due to a very simple change, namely that now the fault plane has a small roughness. Okay, so there are in and out of the plane variations of the fault surface. So we see vastly different degrees of complexity in rupture and radiation due to roughness. And that's actually encapsulated in the temporal rupture evolution and the local slip rate function. So on the top right, I show the final slip and the peak slip rate, as well as the contour lines of rupture time for a similar case. You see it's very complicated for a rough fault. And if we now look into the on-fault source time functions or slip rate functions, SRFs here, we see that they're very complicated. They have secondary peaks. Some look simple, like as the rupture has propagated long distances, the source time functions become simpler, more peaked and shorter. And if you're closer to the hypercenter, they might be very complicated. Now, Tinti et al. Some 20 years ago almost proposed that the Joffe function is a very powerful, useful representation of that slip rate on the fault. And the regularized Joffe function parametrization is now widely used in finite fault simulations. The question is if we can, let's say, modify these nice and smooth Joffe functions eventually to represent more of the small-scale complexity and high-frequency radiation we see on the left in this panel. And I'll come back to this in a moment. Okay, so when we want to build our rupture model generator, we're looking actually in the correlations of the temporal rupture parameters. And usually we use databases of tailor-made dynamic rupture models. What do I mean by tailor-made? That is, we simulate magnitude 6s, magnitude 6.5 or 7 earthquakes, simple fault geometry, add some variations in initial stress or roughness and whatnot, and then look at how do rupture speed, rise time, peak slip velocity depend on each other, or maybe on the slip or on the stress. Okay, so are the variations in rupture velocity correlated with slip, with stress? Likewise, variations in rise time or rupture speed? And how can we constrain these variations and limits, in particular in the peak slip rate? And so using this information, we do correlation analysis to develop kinematic rupture model generators. A first generation was sort of proposed back in 2004 by Guattari et al. Using about 12 or 15 dynamic simulations, looking at some simple scaling laws, correlations between individual parameters, and from that devise a scheme how to get slip, stress drop, and finally the rupture evolution on the fault plane. Schmedes and Archuleta did the same thing for maybe a dozens or 100 simulations of dynamic ruptures. And then there's additional work that came out from Alice Gabriel about 10 years ago, or some rough fault simulations we did not too long ago that show these correlation of, let's say, rise time with slip, or rupture velocity and peak slip velocity. So we use that information to build the rupture model generators. So there are several approaches that use these scaling laws to advance geostatistical tools. And I want to highlight one of the most recent developments here by Savran and Kim Olsen that used about 100 dynamic rupture simulations for about magnitude 7 earthquakes on essentially planar fault with some roughness. And they used geostatistical techniques as sort of shown on the left from variogram analysis and some scaling laws to come up with the kinematic rupture generator KGR as shown, and then get an example simulation on the right from slip, the rise time, and the rupture propagation. We currently, just as an outlook, we currently work on a machine learning-based approach to train such a kinematic rupture generator from dynamic rupture models. So instead of using geostatistics or empirical scaling laws, we use information as shown on the very left from dynamically generated rupture models. We look at the Joffe function behavior and individual points, their spectral characteristics, and inject that into sort of, let me say, a nested machine learning algorithm to then come up with a forward predictor of the slip on the fault and the rupture evolution. So this is work in progress, but what that is based on is sort of an initial set of some 20 or so dynamic rupture models. So I want to take a final look now into the current, let's say, constraints and observations that we may have from recent earthquakes, from observations and simulations. And like every single earthquake, every large earthquake in particular that occurs, keeps surprising us. We always learn something new. There's always something happen we didn't expect. So one small point I want to raise here is that even on what I call quasi-planar faults, small-scale variations, either in stress or in roughness, they lead to very intricate rupture properties, to dynamic triggering, to multiple rupture fronts, to small-scale rupture, supershear rupture episodes, so on a small range area on the fault. So here's just an illustration of that from some previous work with Ripberger et al. We see, rupture nucleates here way ahead of the main rupture front, eventually coalesces, and then we get these multiple rupture fronts that radiate seismic waves in different ways, almost simultaneously from different parts on the faults. The occurrence of supershear rupture, in particular for large strike slip earthquake, has now been more often documented. We saw this very prominently for the Sulawesi earthquake of, I think, 2018, that also created a tsunami because it occurred in a small bay. And Ulrich et al. Simulated dynamically how the supershear transition happened on this fault. And Wenger and Emperor basically developed some theoretical thoughts and the conditions for the supershear rupture fronts to occur. We also have to realize that we see, in particular for earthquakes magnitude 7 roughly and larger, large-scale fault segmentation come into play, which profoundly affects rupture and radiation processes. And I show a very, prominent example on the top left here from New Zealand, the Darfield earthquake of 2010, which activated about 15 or so individual fracture planes on a fault that wasn't really well known in advance. And what we need to realize is how these ruptures then evolve depends on where they nucleate and how these individual segments are oriented within the regional stress field. And a really critical example to illustrate this again is the Turkey earthquake or set of earthquakes in 2023, which I show here the slip distributions that we inferred from geodetic and seismic data for the two events. And here is a dynamic simulation that is by Lee et al. Oh, there's a typo here, it's Lee et al. And point is that the rupture nucleates at a small subsidiary fault that wasn't really well known at that time. But in the regional stress field, the rupture was able to actually branch onto the main East Anatolian fault with some delays, and then propagating sort of to the northeast and southwest at different speeds with different properties, had an episode of super shear in this direction, and then eventually peters out. And now, if that rupture had nucleated on a different point, the earthquake would have looked completely different. And that's something that we do not account in our kinematic rupture generators in the sense of how we choose the initial nucleation point. So I want to stop here with a few final thoughts. I have no conclusions, just a few final thoughts. I sort of hinted to that the current rupture model generators that we have are all based on essentially a single class of earthquake simulations, in the sense that we really used only near-vertical quasi-planar strike-slip earthquakes, sort of in a magnitude range 6.5 to 7.2, maybe 7.5. Did the dynamic simulations for this and used that to inform our kinematic rupture generators. We haven't really looked at more complicated cases, and I think that's something we have to do. In the rupture generators, we tend to avoid dealing with super shear rupture velocity. We may accept it if it just happens to pop out, sometimes to try to avoid it. And so we constrain the temporal rupture evolution not to develop super shear ruptures. And what I'm called dynamic triggering, or these multiple rupture fronts that might occur and coalesce, is something that we don't have in the rupture generators at this stage. What we also are missing out is this multi-scale geometric fault complexity. So we do include roughness, and we train and develop rupture model generators that include roughness, like Safran and Olsen's work, but we haven't included larger scale segmentation, so that if we have multiple fault segments and an individual, first one gets activated, what is the likelihood for rupture to jump over barriers, larger barriers, onto further fault segments? And this is something we can include in the kinematic simulations. And that actually can be extended to considering other variations in fault plane geometry, like listricity, or like variations in the long strike dip of the fault. The way we constructed our rupture model generators as of now does not contain any of that information. And with that, I would like to finish my talk. Thank you very much for listening, and I'm looking forward to the panel discussion a little later.